Welcome to CO450 Computer Architectures. This is week 12. Transmission. A digital signal in a computer system uses a change in voltage to represent 0 and 1, typically from 5 to 0 volts. Low voltage would be seen as being 0 to 2 volts, and this would be used to represent binary 0. High voltage, 3 to 5 volts, would normally be used to represent a binary 1. This leaves a gap in the middle, 2 to 3 volts. This is not used and could cause signal error. It's a grey area, an area where we can't determine whether a signal is a 0 or a 1. The representation would be ambiguous. In radio transmission signals, such as Wi-Fi, the frequency of the signal is used to indicate 0 and 1. So low frequency, 0, and high frequency of 1. And again, we have an interland between the two where we would be unable to determine whether the signal should be a 0 or a 1, or might be misinterpreted from a 0 to a 1 or from a 1 to a 0. So this grey area exists within radio frequency transmission as well as electrical transmission. So this brings us on to transmission problems. Bits can change during data transmission for many possible reasons. Normally this is caused by either electrical interference, and we would get a change in the voltage state between the high and low, meaning that we perhaps change a bit from a 0 when it should be a 1, or 1 from a 0. Or we might get the same sort of interference within radio signals caused by any form of electromagnetic radiation or interference as the radio signal travels through materials. And again, this might lead us to, or the signal to be changed, a bit within the signal to be changed from a 0 to a 1 or 1 to a 0. So we need a way to detect errors that occur during the transmission process. For example, if we're transmitting 1101 and it's transmitted, this is a 13 in decimal, but if we then receive 1100 and that's 12 in decimal, we know that one bit has flipped during the transmission process and the number is now incorrect. But how do we know that this has actually happened if we are transmitting and then receiving? So if we're not at the same end, we're receiving data, we don't actually know what was necessarily transmitted. It could have been that 12 was transmitted, and that's perfectly correct, but actually 13 was transmitted. So how do we know that data being sent is as it was sent, as it hasn't been changed somehow during the data transmission process? So parity bit checking is something that we use to help us with this problem. So parity bits. So a parity bit is a bit that is added to ensure that the number of bits with the value 1 in a set of bits is either odd or even. So parity bits are used as the very simplest form of error detecting code, and here we have a even parity bit being added to 3-bit patterns. So the 3-bit patterns that we have bit 01 and bit 02. And those 3-bit patterns, that's the data we're trying to transmit. And in this table, I have 5 rows there, 5 examples. So in the first row, we have the data transmission part, which is all 1. So 1, 1, 1. Now, in order to use even parity check, then we're going to add a parity bit, which is going to be a 1 bit. Now, the reason it's going to be a 1 bit is because 3 1 bits that are in the data, obviously 3 is an odd number, so to make it an even number of 1 bits, we simply add a parity bit which is set to 1, hence making it an even number of 1 bits in the total transmission. In the second row, our 3 bits that we're trying to send as data, our data transmission, is 001. So we add a 1 parity bit, again because 001, obviously there's only 1 bit there, it's an odd number, so to make it even, we're adding that 1 parity bit. With the third row, we have 110. Now this means that our data is actually even number of 1 bit. So our parity bit we just set to 0 to keep the even parity within the data. Then we have 100. Again, we only have one bit in the data, so we add 1 as a parity bit to it to make it even. And then finally we have again 110, which means that we have to add our 0 parity bit because we've got even number of 1 bits already within the data. So it's a very simple way of working and providing some little error checking here. So for every 4 bits of data that we're transmitting in this case, 3 of those bits would be data and 1 bit would be just there to provide a parity check. And it's important that you note this, that sometimes in data transmissions, and when we get into our networking module later on, you'll see that data that is sent across a network between computers, it's not all there as pure data. It's not all information that is going to the other end. Some of the information and data that's contained within that transmission is purely there to make sure that the data being sent, in this case in a parity check, is actually correct. And it also provides other additional information to make sure that the data being sent across the network is getting from A to B, for example. So there's a whole load of information that we can add to data being transmitted in order to make sure that data gets there correctly. And part of this is parity checks. And this is the most simplest form. So even and odd parity bits. So you could use an odd parity bit check, or you could use an even parity bit check. It doesn't matter as long as both ends agree on what system you are using. Okay, so some systems will use even, some systems will use odd, and it depends obviously on the system that in place, and making sure that the two ends obviously are talking the same way and using the same scheme. Normally it's an even parity check. So if we saw data being transmitted here as 3 ones, as we said, that's an odd number of 1 bits within that data, so an even parity check would add 1 to it. In an odd parity system, of course, we would be adding 0 to it because it's already an odd number of 1 bit, so it would be adding 0. And we're adding this parity bit into the most significant bit position, which is the far left of the data. So the most significant bit, the MSB, is being changed to, well, it's been added to give that parity check. So in the first example it's 1, in the second example it's 0, whether you're using an even or odd system. If the data we're trying to transmit was 101, then in that case it's already an even number of bits. So an even parity check, we would make it a 0 for the parity check. For an odd, we'd make it a 1. So it would be different to the first example, in the reversed around the other way. So it depends on the data that you are transmitting. So here we can see, again, it's just some more examples of even and odd parity bits. So I've got 2 columns, one showing an even parity check and one showing an odd parity check. And again, we're using the most significant bit. We're using 8 bits here in total, but only 7 of those bits represent data. So we have 7 bits of data. That's the information that we're sending from end to end. We're adding a parity bit to it in bit 8, which is the most significant bit, and as illustrated by those numbers that are in red here in the example. So those are just parity bits that are being added to the 7 bits of data that we're actually trying to transmit to indicate whether we're using even or odd, or we're using an even or odd scheme. So in the first example, we're just sending all zeros. So all zeros would be an even number. So we just simply add 0 under an even scheme. Under an odd scheme, we'd add 1 as our parity bit. In the second example, we've got 1 0 0 0 1 0 1 as our data. So in the first, under even, we would be adding 1 because there's only 3 1 bits within that data. Under an odd system, we would be using 0 because we keep it odd. In the third example, we've got an even parity bit because we've already got 4 1 bits within our data, so that means it's even already. So in odd system, we'd have to add 1 to make it an odd number to being, to be correct for an odd scheme. So whether you're even using odd or even, you have to obviously set the parity bit correctly for that on transmission. So when transmitting data, the system needs to know what parity is being checked for, even or odd. The size of the data packet, which is used to send the data, will obviously increase when we add this parity bit. So at the moment, we're only using a single parity bit check, so we're only increasing the data that's being sent by 1 bit. But it does mean that if we were thinking about how we're going to transmit our data and the amount of data we can transmit at any one time, we now have to allow for that 1 bit of parity check that we're doing per packet length, so the data we're sending. So we don't tend to send all the data in one go. We normally break it up into discrete segments, and those segments we come together to form packets of data that are being sent over a network. You'll learn more about this when we get into our networking module, but essentially not everything's sent together. So in this case, we're sending 8 bits at a time as a data packet, but part of that packet of data, 7 bits are data, and 1 bit is our actual parity check. Now, how do devices then check parity? How can they check this? Well, you can actually use logic, and one of the best gates for applying this type of logical check to signals would be an exclusive OR gate. So an XOR truth table is what we have here. So an exclusive OR, you only get 1 if the 2 inputs are in an exclusive OR position. So 1 or 0 or 0 or 1, basically. So as you can see, 0, 1 or 1 or 0 produces 1 as an output. 1 and 1, which would normally under a normal OR gate situation or logic gate, that would produce 1 as well. But in an exclusive OR, it doesn't. So when all the inputs are 1 or all the inputs are 0, we only get 0 on the output with an exclusive OR gate. So we can use this to check whether there is an odd number or an even number of bits within our 2 bits that are going in this case. So you can see there, so an odd number where we have 1 0 or 0 1, for example, so an odd number of 1 bits in both those ones, they're producing 1 as an output. When we have an even number, 1 1 or 0 0, then we get 0 on the output. So it's using that to check through the logic of an exclusive OR gate whether we have odd or even. And we can use these exclusive OR gates to check a whole word length. So in this case, I now have 4 bits, as we can see, A, B, C, or D, and they're providing inputs 2 bits at a time into an exclusive OR gate, which are brought back together into another exclusive OR gate, which would be able to check then for even parity within our word, or even odd or parity, effectively by checking this through. And we could build this little circuit just to show you that, and it might be a good idea just to do that so I can show it live in multimedia logic. So I'll just switch to multimedia logic and we'll just create this little circuit. Okay, so here we are in multimedia logic, and I've just built that circuit using exclusive OR gates. So we have our word here, 4 bits coming into exclusive ORs, 2 bits at a time, and being brought back together with another exclusive OR gate to an output. And at the moment, that is set to all zeros. So if I set the first bit here to 1, so we have 1 and then zeros, we notice that light comes on over here. So this represents 1. So it adds a 1 parity. So if we assume this is the parity bit, then we can set it by simply passing through the XOR gate. So if I put 2 bits as 1 now, so 1 1 0 0 in our word here, then that's an even number of 1 bits. So our parity bit is 0. And if I set it to an odd number, so 1 1 1 0, then we get a parity bit of 1. So we can see we can either use it to generate a parity bit, as we're doing here. So the 5th bit of our data transmission could be set to whatever output comes out of this, so 1 or 0, so 1 indicated by the lamp being lit. Or we could check it at the other end. So coming in, we could check the bits coming in and see if we're using even parity check. We know that if we get a 1 here, then we've got a problem. So if there's as a parity checker and we're using even parity, then we know if we get a 1 here, we've got an issue, because the word coming in obviously has an odd number of 1 bits within it, and that shouldn't be the case under an even parity checking system. So we can either use it to check or we can use it to generate. But the point is that we can use logic gates, which are very easy for obviously our computer to utilize to check the bits for a parity system, or generate a parity bit or check a parity bit in terms of the word coming in. So this is good. So we can check an error. We obviously couldn't correct the error using this system. It's worth pointing out. We just know that there's an error. We don't know where it is. So it's not going to help us in terms of determining where the error is. What we would normally do is simply ask for a retransmission of that packet of data. So if data comes in and it's got an odd number of bits that are 1 in it, for example, and we're using even parity check, we know that something's gone wrong within that signal and that data transmission, so we need to actually ask for that packet of data to be resent. So we wouldn't try to correct it using this scheme, because we can't identify which bit has actually changed. We just know that there's a problem with it, and we'd ask the other end to resend that. And when you start to think about things like that, then you start to realize some of the complexity in sending data from one computer to another computer, because, as I just said, we would need to ask for a retransmission. So how do you then ask for a retransmission of data if you find an error? And that's a whole nother area of networking, which we'll be looking at in the networking module, for example. So data has to go backwards and forwards in order to do these checks, and also to ask for resubmissions of data and so on if they are in error. But we're interested in the parity side at the moment. Let's come back to the slides. So even or odd parity schemes, systems need to be in place at either end in order to check those bits. So an even parity generator produces a logic 1 at its output if the data word contains an odd number of logic 1s. If the data word contains a even number of logic 1s, then an even parity generator will produce a logic 0 at its output, as we've just demonstrated within our working version of this circuit within the multimedia logic. So simple even parity error detection then. So in this example, the number of 1 data bits is even, so the parity bit is set to 0. By contrast, in this example, there are an odd number of data bits, so the parity bit then becomes set to 1. So we have 2 examples here. One has an even number of bits in the data, so we set the parity bit to 0. One has an odd number of parity bits within the data, so we set the parity bit to 1. So if we assume that after being transmitted, the lowest weighted bit of the previous byte, the one on the far right, had fallen victim to interference, either electrical or within the radio signal, depending on how it's being transmitted, and if it changes in what's received, so it flips from a 0 to a 1, the parity bit in this case no longer corresponds to the bytes parity. So an error is detected. So we're detecting the error, but we're not able to understand which bit has been impacted, essentially. So we know there's an error, we just don't know which bit it is. So if 2 bits or an even number of bits had simultaneously changed as the signal was being sent, no error would have been detected. Now this is really interesting, because this is the big flaw within this simple parity checking system. So if 2 bits change, if they both flip, so the first bit flipped from a 0 to a 1, and the second bit flipped from a 1 to a 0, in that case, then the data that comes at the other end appears to be without error. But we know, because we've just done it, we just flipped those bits, we know that there is an error that's been taken care of. So the thing about this simple even parity detection system is, if 2 bits change, then potentially we can't, we'll still think it's correct. It doesn't just pick up all the errors. So we could still have data which is essentially incorrect, even with this system. So it's not a very robust system. It only picks up on single error checks, and we won't be able to put it right. We'd have to ask for a retransmission of the data. So as the parity control system can only detect an odd number of errors, it can only effectively detect 50% of all the errors that there could possibly be. So this error detection mechanism also has the major downside of being unable to correct the errors it finds, and the only way to fix the problem is to request that the erroneous byte be retransmitted. So these are the limitations of it. Now this doesn't suggest, this shouldn't really suggest that it's a very poor system, 50% of all errors, because it's very unlikely that you're going to get enormous amount of errors in your system. So if your system is robust and it's reliant on the cabling is correct and the data transmission from either end is correct, if it's a robust system, then you're not really going to get you shouldn't have high number of errors within your data transmissions. So having a simple even parity detection system like this may be absolutely fit for purpose. So we talk about fit for purpose and tolerances. It's just a note that this is the tolerance of this one is 50% of all errors, and we're unable to correct those errors. However, it still might do the job perfectly adequately within a system that is robust enough where you only get the occasional single bit problems. So error detection. So if we look at the example transmission below, the parity bit can be computed as follows, assuming we are sending a simple 4-bit value 1001. With the parity bit following on the right, with the chevron denoting an XOR gate. So transmission sent using even parity. So in this example, we're sending 1001, and our parity then is being generated. So computer A wants to transmit 1001. It computes that the parity bit then value required under an even system would be 0 in this case, adds that to the data being sent. Computer B then receives the message, so it receives 01001. It then computes parity again using an even parity system, and it comes up with 0, which then means that it must have the correct data. So we're expected to get a 0 parity bit generated under an even parity system, because the parity bit included within that data indicates that we have an even number of 1 bits, which we do. So that example is correct. Using odd parity, so if we're using the same data, so 1001 again, computer A would compute the parity bit. This time it would be 1 under an odd system, add that to the data and then transmit. Computer B would receive that. It would then put it through its own parity check, and it should come up with 1 as an output. So put it back through its even parity check, and we have 1. So 1 indicates which we'd expect as an odd result. So it's an odd number of bits, which under an odd system, of course, is what we're expecting. So it means the data is essentially correct. So this mechanism enables the detection of a single bit errors because of 1 bit gets flipped due to line noise. For example, in an electrical system, there will be an incorrect number of 1s in the received data. So again, if we're using even parity here, we might transmit now 100. We transmit with our parity on that, but there's a transmission error. Now it's flipped one of the bits, so it's flipped what we got, bit 0, bit 1, bit 2, bit 3 has flipped from 0 to 1, and then when it's computed using even parity system, we get a 1 as a parity output, which means it's an odd result. So we're expecting an even result using our even parity set. We know we've got a problem here, indicates that we've got an error, so that'd have to be retransmitted. So a parity bit is only guaranteed to detect an odd number of bit errors. If an even number of bits of errors, the parity bit records the correct number of ones, even though the data is actually corrupt. So in this case, we're sending again the same example. So 1001, create our parity value of 0, add that to it and transmit. But in this case, bit 0 and bit 3 have transformed. They've errored within the transmission, going from 0 to 1, but because both of them did, it actually looks as if we've got the correct data when it's run through the parity check at computer B's end. But in fact, that's actually incorrect. So just shows the limitation of the checking system. So week 12, we do have our little exercise sheet for this week, which gives you a couple of examples for this, which will come up in the TCA. So it's good to have a little practice on those. So we'll just switch to the exercise sheet. So here we are in the exercise sheet, and we've got an even and odd parity checking. So it says, using an even parity bit check, check the following data transmissions by adding your own parity bit in the empty column and ticking the appropriate result. So it does state that we're using even parity bit check here, and obviously for TCA questions I will of course indicate whether you're looking for even parity or odd parity. So we're not expecting you to just to assume one or the other. We will clearly state which is being utilized. So this is using even parity. So with even parity, we're just looking for an even number of 1 bits. Now we can see in the first one here, we've only got an odd number of bits. So our parity check would give us a 1 to make that even, which means that we've got an error. So there's an error in this transmission. Here we need to make this check again. So we're checking for even parity. We've got an odd number of 1 bits. So our parity check would come back with 1, which means we've got an error. Next one, we've got an even number of bits within the data transmission. So our parity check would produce a 0, which means it must be correctly transmitted. And then finally, again, we've got 4 1 bits there. So again, our 0 parity check will come up, and that must mean it's correctly transmitted. In the second question here, we're using odd parity bit checks now. So we're doing the opposite. So we're using the opposite way around. So we're looking for odd numbers. So here we have, first example has 5 1 bits in it. So that is odd. So again, the odd parity check on this would require us to, if we were doing error detection on that, it would produce a 1, which would indicate that we have correctly transmitted in this case, because we're using an odd parity check system. So in this example, we've got 3 1 bits. So again, even parity check would produce 1, but the data is actually being correctly transmitted. Now we've got 1, 2, 3, 4, 5, 6. So again, this would be 0. So this would be error under an odd parity system. And finally, we have 3, which would give us 1 as a parity check. So again, that would be correctly transmitted under an odd parity system. There we go. So just some quick examples there of data checks. So it's important that you just understand it's either even or odd, the parity checking on that. And it's just literally looking at the number of 1 bits within the data that's being transmitted, determining whether it's an odd or even number of 1 bits. And depending on whether you're using even or odd scheme for your bit checking, determines whether it's going to be correct or incorrect in terms of errors being detected or not. So it's as simple as that. I think sometimes students sometimes worry about this parity checking and perhaps think it's going to be more complex than it is, but it is literally just the number of 1 bits, whether it's an even number or an odd number, depending on whether you're using odd or even scheme, and that is your data check. So it's as simple as that, really. Okay, so we'll come back to the slides. So in the first little example, so our first sort of parity checking system, it's very good for single bit errors, but we can't detect those errors. We can only determine whether there's an error has occurred. We'll have to ask for retransmission. But there are systems that are a little bit more complex and require a few more bits to be added for the checking, but they allow us to actually check and determine whether there's been errors and where the errors actually are, and we can actually start to actually make some corrections to the data that's come through potentially. So this introduces the idea of two-dimensional even parity scheme. So this particular scheme can detect and correct a single bit error. It can detect but not correct any combination of two errors in a data packet. So the way this works is that it takes the data. Now the data here is shown in the grey squares, and the parity bits are shown in orange here. Now the key with this two-dimensional parity checking system is that we split the data up that is to be transmitted, and we lay it out in this sort of stacked grid, and then we are checking we're not using just one parity bit now, we're actually checking the parity of the individual rows and columns within that data. So we arrange the data into essentially an array, rows and columns, which we then check the parity of each row and each column, and if we get an intersection of parity issues, then we know which bit is problematic, is how it's going to work. But I'll just step through this example here. So we take the transmitted data, split it into even segments, placing each segment on top of each other from the left to form rows in a matrix. So here we've got our data, and we split it up into even segments. So we have 5 bits per segment of the originally transmitted data, and we split those segments up and put them into this matrix, and then we are adding parity bits to each row and each column. So first of all, we check the rows. So using even parity, we can see that we put a 1 bit here for the parity bit. Next, let's just come back a bit. So this is the original data. So if we had, so we've got 1, 1, and 1, so we've got 3 ones there, so we add 1 as a parity. Here we've got 4 ones in the next row, so we add 0 as our parity bit. Next we have 3 ones, so we add those as a 1 as our parity bit. Then on the columns, we have 2 ones here, so we have 0. 2 ones here, so we have 0. 3 ones, so we add 1 as our parity bit. 2 ones, so we add 0 as the parity bit. A single 1, so we add 1 as a parity bit. So we have parity here, and we should find that we have parity also then in this row and this column. So this 0 bit here indicates the parity check for that. So this data is then all transmitted together, and then it's put back into the table, into the matrix at the other end, and now we should be able to identify a single bit error by the intersection of those parity bits. So we can see here, if we look across, if we check the parity of this row, then we'll find that we'll get our 0 essentially, because that's correct. Yep. So it's been transmitted correctly. Here we were expecting a 1 as our parity bit, but we've actually got a 0. So that's potentially an error in this row somewhere. This row is correct. We've got 1 bit there, and then if we work along the columns, we find this is correct. This is incorrect. We're expecting a 1 parity. We've got a 0. This is correct. This is correct, and this is correct. So we know by the intersection of this row and this column that this bit where the 2 intersect, that must be the bit that's flipped. Okay, so by looking at it in terms of rows and columns, checking the parity, we know that we've got an output. We've also got problems as well in terms of our output here. So we should have, with this, we've got a 0 here. So we've got an output issue in terms of the overall parity checking of this two-dimensional check. So a double bit error, however, so if we have a double bit error in data transmission, then we can still detect that, because here we can see that we have the wrong parity bit. So we have 0 parity rather than 1 parity, which we should have for these two columns. The rows themselves are correct in terms of parity, but we've got two problems there. So we know we've got an error. We couldn't detect which ones these are, though, because we don't have that intersecting row, and we have two errors within it. So with double transmission errors within our data, we can't detect it, but we could resend or ask for a resend of that transmission. That's what we would do. So with two-dimensional parity schemes, we again have a little way of testing this. So in your exercise sheet for this week, again, we have that little test on that. So I'll just switch to the exercise sheet. So here we are in the exercise sheet. So two-dimensional even parity scheme. So it says to check the transmissions below with a two-dimensional even parity scheme by adding your own parity bits to the rows and columns and ticking the appropriate results. If you do identify a single bit error, reference which bit has the error by entering its row and then the bit number. So let's have a look first of all. So do our check for even parity on this first row. So we have 4 1 bits there, so the parity bit should be 0. And then next one we have 2 1 bits, so parity again will be 0. Next one we have 2, so that's parity 0. This one has 3. So parity will be set to 1. And then if we go on the columns, so 2 1 bits there in that first column, B5, B4, 2 1s, yeah, 2 1s, 2 1s, only 1. So that is our issue. And here we would have to set that as 1, so to indicate we have an error on both the column and the rows there. So we know we've got an error. Is it correctly transmitted? No, we've detected an error. Can the error be corrected? Yes, it can. Error can be corrected, and the error is in the intersection of R4 and B0. So R4, B0 would be the correction that we would need to make. Oops. There we go. R4, B0. And what about the next one? So even parity check on this. So 4 1s in that first row. So 0 is the parity bit. Next one we have 5 1s, so we need 1 to make it even. 4 1s, so 0. 2 1s, so 0. And then going across the columns, all 0 is 0. 2 1s there. 4 1s there. So 3 1s, that's not even, so 4 1s and 2 1s. There we go. And again, we've got an error overall here. So effectively, it's the intersection of R2 and B2. R2, B2. So this bit here, sorry, this bit here, R2 and B2. This is the bit that's flipped. So it's not correctly transmitted. An error has been detected. We can correct it. Error can be corrected. And to do that, we need to look at R2, B2. There we go. Now again, we could use the two-dimensional parity checking with an odd parity scheme as well. So if we check the transmissions here, we're looking for odd. So again, I'm just going to use the parity check, the even parity check to work that one out. So that was with 1, 3 1 bits. That would also give us 1, 4 1 bits 0. Would give us 1, and then the column 4 1 bits there, 1 bit there, 1 bit there, 1 bit there, 1 bit there, and that would also be 1 bit. Right. So this time it's the intersection of the zeros that we are looking for here, because they represent the errors effectively. So our error here is in R3 and B5. So R3, B5. Is where we've got an error. So we can correct that, and we've detected it. So error detected, can be corrected, and R3, B5 is where that error has occurred. And if we come down, then again, what have we got here? So odd system. So 4 1 bits there. So in that row, so 0. That's even already. So that's okay. Makes it even. Odd. And that one is odd already, so 0. Sorry, that should be 1. Yep. And on this side, 1, 1, 1. Oh, that one's even, so that should be like that. That's it. That's it. And that's it. Right. Okay. So again, yeah. So again, we can see the zeros here. So effectively, R1, B3. So R1 bit 3 is where the error is. Okay. And that's it. Right, so we go back to the slides. We go. So hopefully you got that. So single bit errors, very straightforward. With a single parity bit, we can check for an error, but it can only detect a single bit error, and only 50% of the errors would ever be detected, because double bit errors it potentially can't check for. And we would also ask for a retransmission of all the data in the data packet is the only way to address that. With the two-dimensional scheme, we can check for single errors, and we can potentially correct them. With double errors, then again we couldn't correct them because we wouldn't be able to identify where they are, but we can again ask for the retransmission of data. So with a two-dimensional system, a parity checking, we can be a little bit more corrective. We can correct a single error at the receiving end, but we still have to ask for retransmission of data with double errors detected. And again, we either use an even or odd system in our parity checking role. So again, both ends will need to agree on the scheme and the system they're using.